Hello everyone, and welcome back to this Nanophotonics and Plasmonics course. In the previous video, we introduced Max's equations and derived the wave equations from the Max's equations. We discussed some of the fundamental properties of these wave equations and fundamental framework, and we introduced the concept of constitutive relations that will constitute the core of light-matter interaction. So far, we discussed the time-dependent fields, where we have an electric field and magnetic fields that oscillate in time. But in fact, this is more convenient to actually go into the spectral domain. So time-dependent fields, like an electric field, which is function of the position and of time, can be also represented in a frequency domain as a function of the position and the frequency, or in this case, angular frequency omega, in the form of a spectrum, just simply using a Fourier transform. So this is just an example here where we have the relationship of this spectral representation of the electric field, starting from the temporal representation of the electric field and having this Fourier transform on top of that. So in the end, when you have a time varying electric field that oscillates in time and in space, you can actually take the Fourier transform of this electromagnetic field, whether if it's electric or magnetic, and actually get a spectral representation where you have a field intensity or field strength as a function of different frequencies or different wavelength. So because the electric field or the magnetic field, so we're going to focus more on electric field in this particular case, but this is also true for magnetic fields. Those are real valued fields. So therefore, when you take the Fourier transform, then we obtain complex valued fields, complex numbers. So we're going to have to pay special attention to the fields and their complex conjugate. And this is the relationship between the two of them when you just change the sign of the frequency variable. So because we use Fourier transform to change those fields into their spectral representations, this has also an impact on Max's equations, and we can actually apply the Fourier transform onto Max's equations and obtain their spectral representation as well. So these are the four Max's equations in the spectral domain. So where we have the curl and divergence operators applied onto the complex fields, electric and magnetic fields, which are now dependent on the frequency. So you will see that because, as a result of the Fourier transforms, now the time derivatives, the special derivatives, and the time derivatives are actually modified. So the time derivatives in the spectral domain now become this I omega, where I is the imaginary unit number. So for some of the applications, it is more convenient to actually work in the spectral domain rather than in the time domain. So we see in the chapter talking about numerical methods that some numerical methods actually solve this form of Max's equations rather than the temporal form that we've introduced in the first video. Something we also have to pay attention to is that if you solve Max's equations, for instance, in a frequency domain that we're going to be discussing in the method chapter, we can actually come back to the temporal representation using the inverse Fourier transform. So this is the inverse Fourier transform expression of a spectral representation field into a temporal representation field. So we can do back and forth transformation of the electromagnetic fields between the time domain and the spectral domain. So this will be discussed extensively in chapter 7 when we're going to be talking about numerical methods. So on a side note, it is also sometimes favorable to decompose a field, whether if it's electric or magnetic fields, into a parallel and orthogonal components. So this is just a mathematical construct. It doesn't carry any physical meaning per se. So this is just more convenient to treat those two components separately, especially when discussing about boundary conditions that we're going to see in a moment. And in this particular case, this is something that which is used in numerical methods as well. So because we deal with complex physical quantities, the dielectric permittivity will also be complex. So we're going to have dielectric permittivity epsilon right here, and actually magnetic permeability mu that will also be complex. So with that in mind, we can actually rewrite the frequency domain, the frequency dependent Maxwell's curl equations, which are given here, and we can actually obtain this new expression here, which is the wave equation in a complex spectral form. So we can actually rewrite this wave equation here. We can actually look at this particular term, and in fact this is homogeneous to dielectric permittivity. So you have the actual dielectric permittivity as we introduced before, epsilon, and we have this imaginary part. So we have this imaginary unit number I, and then you have this term sigma, which is a conductivity function of omega and epsilon naught, and this whole term now in turns constitute this complex dielectric permittivity. So this complex dielectric permittivity epsilon is just composed of a real part, the previous epsilon we introduced before, and this imaginary component here. So we can rewrite those wave equations for linear, isotropic, and inhomogeneous media into their spectral representation with complex spectral fields. So we have the electric and magnetic fields. We have the currents that are also complex, and then we have these complex terms that show up here due to the Fourier transforms, and the epsilon and the mu that are showing up in those equations are now the complex dielectric permittivity and magnetic susceptibility. So something which is also very, very important when dealing with nanophotonics, we're going to have to deal with different materials, and therefore we're going to have interfaces between different media, and therefore we're going to have to pay special attention to how Maxwell's equations or the interfaces between two different media, how the electric and magnetic field behave when crossing those boundaries, those interfaces. Those equations need to satisfy those boundary conditions for any type of discontinuity, which are just basically interfaces. So what's the deal here? So in fact, we cannot necessarily use differential form of Maxwell's equations. It's very difficult because of the discontinuity of the mathematical form of these Maxwell's equations in their differential form. So in fact, we have to actually use the integral form of Maxwell's equations, which is way more convenient. And you can actually transform the differential form Maxwell's equations into their integral form using a combination of Gauss and Stokes theorems. And these are simply the time domain, the time-dependent Maxwell's equations in their integral form. So we have the four equations linking the electric field, magnetic flux, electric displacements, and magnetic field as the differential form. But this is now in their integral form. So we can actually show mathematically, and something which is not going to be done here. These are things that are actually shown in different textbooks on electromagnetism. You can actually show that those equations lead to boundary conditions that are expressed as a set of four small equations. So we have two small equations here, and then we have another two equations here. So there are four equations that are relating the different components of the electric and magnetic fields. So the first two equations that we obtain here show that basically, so n in this those equations stands for the vector normal to the actual interface between two different media. Those two first equations here show that the electric field, the tangential component of the electric field, is continuous at the interface. So if we want this condition to hold when the electric field is tangential to the interface, meaning that basically when this is orthogonal to n, in order to satisfy 0, E sub I, so the tangential component of the electric field in medium I, just at the interface, and the tangential component of the electric field in medium J at the interface must be equal, which basically means that the electric field and the tangential component of the electric field is actually continuous across the interface. The same something similar. The second equation here. So this is basically the K represents a current density at the interface, and this second equation also discusses the continuity of the tangential component of the magnetic field H across the interface when there's no current. So if K in this case is 0, then H is the tangential component of H is continuous. And the second set of equations that is looking at the normal component, give you the normal component of the electric displacement and the magnetic flux or magnetic induction. And the same, they're looking at the continuity of the normal component of those two physical quantities. So the electric displacement is continuous when there's no charge, no surface charge at the interface, when sigma is 0. So why those boundary conditions are important? This one simple example has to do with interfaces, of course, and there's a lot of cases where interfaces play a huge role in nanophotonics. One of the key examples, for instance, is that if you have a substrate and you have any type of nanoscale system, whether if it's a molecule, a quantum dot, a nanoparticle, or a more complex geometry and structure supported on the substrate. So the substrate constitutes an interface, at least between a glass substrate and air surrounding medium or water. And light, as an electromagnetic field, will actually see this interface and will behave according to these boundary conditions. So let's consider, for instance, a simple case of a plane wave, which is expressed as is, which has a certain field strength, an amplitude E1. It's an exponential form. It's propagating along K1. So K1 is the wave vector. It gives you the propagation direction in general, a certain frequency omega. So it's oscillating the frequency omega, propagating along a certain direction K1. And it has a certain amplitude, the amplitude of the wave, which is given by E1. So this is just with an arbitrary polarization, and E1 can be always written as superposition of two plane waves, two separate plane waves with orthogonal polarization. So E1 can be decomposed into two separate polarizations. So I've touched upon this in a side note just before. And it's something general. In this case, we just label those two components as rather than parallel and perpendicular, but as polarization S and polarization P. So S and P labels come from German terms that are actually meaning parallel and orthogonal. Parallel and orthogonal to the incident plane. So let's look at this with a specific case. So we have here an interface which is located here with the normal along the z direction. This interface is actually separating two different media, epsilon naught mu 1, epsilon 1 mu 1, and epsilon 2 mu 2, whatever those media are. You have this incoming E1 plane wave, so you can split this into different components. We have the S component, the polarization, which is basically orthogonal to the plane of incidence, which is defined by the k vector of the plane wave here, and the normal to the interface. So this is pointing out of the screen, while the incidence of plane of incidence is in screen. and the parallel or P polarization here. You see that the field, the electric field, is actually in plane with the plane of incidence. So these are the two orthogonal components of the field E1. So we can actually from there apply the boundary conditions that we just defined. So looking at the continuity of the tangential component of the electric field and the continuity of the normal component of the electric displacements, which is the dielectric permittivity times the electric field. We can actually calculate and determine the reflection and transmission coefficients. So we have here the reflection coefficient and the transmission coefficient for this wave E1s as this wave arrives at the interface. So we have the wave which is being transmitted here. So we have E2 with a polarization S. We have E2 with E1 with a polarization S, which is being reflected by the interface. So these coefficients dictate what relationship will be linking the transmitted wave, the reflected wave, and the incident wave. The same for the other polarization. We have a reflection and transmission coefficient for those transmitted and reflected wave with respect to the incident wave. So we're not discussing how we actually obtain those coefficients. This is something that you can find either in a Novotny textbook, Principles of Nano-Optics. It's page 20. If you have the latest version, version number 3, or any other electromagnetic and even optics textbooks. So I strongly encourage you to actually recover those reflection and transmission coefficients, which are also known as Fresnel coefficients, starting from this randomly polarized plane wave, applying the boundary conditions. So you can recover those coefficients. So why does this matter? Simply because if you shine light in experiments onto a substrate, where you're going to have some light is going to be transmitted, some light is going to be reflected, and these coefficients dictate what's the amount of light that will be reflected and what's the amount of light that will be actually transmitted through the substrate. So we'll see some applications of that. We'll actually do some live demo about transmission of light later on. We're going to be talking about total internal reflection. We can actually see in application these particular Fresnel coefficients. So now the last piece I want to cover in this video concerns the conservation of energy. So conservation of energy is basically governed by the Poynting theorem. So although it's not a direct consequence of Maxwell's equations, but Poynting theorem can be actually derived from them. So it provides a clear relationship between the electromagnetic fields and the actual electromagnetic energy those fields contain. So you can work through the math. It's long and lengthy, but you can actually obtain this relationship, the Poynting theorem, in this very general form, as it's shown here. So this relation here, you don't have to memorize it. It's long. There's a lot of term. It's not necessarily critical to actually memorize this equation as is. What matters from this equation, which is just a direct conclusion of Maxwell's equations, is basically the physical meaning of each of the terms constituting this relation. So the first term of this equation, of this relationship, is this integral over the closed surface encapsulating a certain volume V of the electric field and the magnetic field, and this constitutes the net energy flow in and out this particular volume. The second term here, shown in red, is the time rate of energy change inside this given volume V. So you're looking at the time variation. That's why we have this time derivative here of electromagnetic energy given by this term that we're going to be discussing in a second. And then we have this integral over the volume. And the sum of those two here is equal to to this term in blue. So this is a very long term that contains multiple parts, but this total term gives you the total rate of energy dissipation inside the volume V. So this is something which is inside the volume. So this is the energy dissipation inside the volume, which is lost not via a flow out of the volume, but by dissipation. So this Poynting theorem basically states that in a given volume, so here in a given volume V, the decrease in the electromagnetic energy per unit time is equal to the sum of the work done by the field forces and the net outward flux per unit time. So you can actually interpret this and break down two main contributions. We have this energy flux density, which is given by the Poynting vector, the term given here in green, where the cross product of the electric field and magnetic fields actually is what we name the Poynting vector. So this energy flux density has a given direction. So we are looking at how the energy flux is oriented with respect to the volume and to the surface. The second term, which is the density of electromagnetic energy, which is given here in the red part of this relationship, the Poynting theorem. Here we have this term in bracket here, which is the electromagnetic energy density W. So if this medium is actually linear, if it's a linear medium and it's non-dispersive, you can actually simplify the Poynting theorem to a much simpler expression. So here we have the Poynting vector. So that was the first term in green in previous equation. We just substituted the cross product of electric and magnetic field by the Poynting vector. Now we have this rate of energy change inside the volume. We just introduced the energy, electromagnetic energy density, and then we have only this last term, which relates to dissipations inside the medium. So these are basically ohmic losses, or Joule effects. So a quantity which is of interest beyond just the Poynting vector is actually the time average Poynting vector. So this is really needed in a lot of applications, in particular if you want to evaluate how the radiation is actually being emitted. So if you want to evaluate a radiation pattern, even for just a regular antenna, you need to actually look at the time average Poynting vector. So you can actually calculate the Poynting vector the time average Poynting vector for this particular case, and this is the expression you actually obtain. So we have to pay special attention because the complex fields, now we have this complex conjugate of the magnetic field, and we have the real part of this cross product that shows up. So if you want to look more into the details for a different type of materials, which can be dispersive and lossy, you have more information on page 24 of the Principles of Nano-Optics by Novotny, that provides a more detailed insight into those specific media.